So we have been talking about rings and had said some things about ideals in particular. And so an ideal is a subring with a nice property so that one can take the quotient by it, so that one gets again a ring. And so we want to see this. So here. So we take an ideal, a ring, an ideal, and then really if I take just I with the addition, this is a normal subgroup. Of R with the addition, because after all R is commutative with addition, and so we can form the quotient group R of I. So set of all cosets. And so this is obviously a group with addition. And so as R is commutative, R mod I is a commutative group. And so we want to make this with the usual addition. And so maybe I just write X for the coset. And so we want to make this into a ring by defining the multiplication in the obvious way. So position if I take this set I with the addition and the multiplication defined by X times Y equal to xy is a ring. Okay, so the main thing obviously to see is that the multiplication is defined. And so we can also say just for completeness, obviously the sum we already have defined. And the natural projection from pi from R to R of I, which sends an element to its coset is a surjective ring homomorphism. Okay, so we have to so here everything is clear. So if this so the only thing we really have to check is that the multiplication is well defined. So to show product is well defined. And so we somehow have to use that we have an idea. So x is equal to x prime and y class of y is equal to that of y prime. Then that means that x minus x prime lies in I and y minus prime lies in I. So we have to see that the class of xy is equal to the class of x prime minus y prime, so we have to see that this difference lies in I, and we can write this as wanted, say x minus x prime times y plus x prime times y prime minus 1. So I hope I got it right. So we have just added this term and subtracted it again. And so this is an element in I, this is an element in I, and by the property of being an ideal, so to be an ideal means that the subgroup in addition, the if you multiply with any element in the ring, you stay in the ideal, we see that this is an I. And so the multiplication is very different. And so the rest is clear associativity and distributive laws follow from those in R. And the formula that we have written down here says precisely that pi is a ring homomorphism, and by definition it is surjective. We had before this thing, if we have a surjective ring homomorphism, then we have bijection between the ideals of the image and the ideals of the source, which contain the kernel. So I should also say it is surjective ring homomorphism, obviously with kernel. By definition, we have that x is in the kernel of pi if and only if phi of x is equal to the unit element, so that means x plus e is equal to e, which is equivalent to x is an element e. We're going to exercise that, and so we get as a corollary there's a bijection in the ideals in R mod I and the ideals in R containing R. The usual, just an ideal is sent to its inverse image. So as we had seen before. Okay, so this is very simple. And then we have, as usual, a version of the homomorphism theorem with the same proof as before. So phi from A to B will surjective ring homomorphism with curl I then there exists, or maybe I just then, if I take phi bar from A mod I to B, which sends the class of X to phi of X, is an isomorphism of rings. So phi bar is well defined as surjective. So just if we have that class of X is equal to the class of Y, if and only if X minus Y lies in I by definition. Because, so, you know, where I mean by X, obviously. So this is if and only if, as this is the kernel, this is if and only if phi of X equal to phi of Y. And so that says it's very defined and injective. And by definition it is surjective. By definition, phi bar is surjective. And clearly, by definition, it's also the ring homomorphism. So that's quite simple. So anyway, but so this homomorphism is never very complicated, but it's a useful thing to know. So, okay, now we want to talk about two special classes of ideals, which are prime ideals and maximal ideals. So, it's just if you have a so you could say it like this, if, you know, so prime ideals and maximal ideals. So if you have an ideal in a ring, then we can form the quotient ring, and it seems in some sense an ideal in a ring is particularly nice if the quotient ring will be nice. And so the nicest rings that we know are integral domains and fields. And so an ideal such that the quotient ring is an integral domain will be called a prime ideal, and an ideal such that the quotient ring is a field will be called a maximal ideal. Or you can also say it directly what it means. So, maybe we will usually want to, I mentioned that we wanted to assume mostly that our rings are commutative. Maybe from now on I will make this the convention. So, so from now on, assume, unless I say otherwise, that all rings are commutative. Consider commutative with one. And for ring homomorphism, A to B, assume U of 1 is equal to 1. If we want to consider something else, we have to say. So, definition, an ideal, so in ring R is a prime ideal if it has the following property. So if whenever we have that a product AB is an element, so the ideal for P, if AB is in P for some elements in the ring, then one of them must already lie in P. By definition, we know that if you have a product of two elements in the ring, such that one of them lies in the ideal, then the product must lie in the ideal. But now we are asking for the converse. And that's not this. And an ideal is called maximal if it is maximal, so it's the biggest possible ideal, which is not the whole ring. So an ideal M in R is called maximal ideal if there is no ideal I. So I want to say it should be an ideal in R, but it should not be R. So that R is not considered to be maximal ideal of itself. So if there's no ideal I, which strictly fits between with M is contained in I and this is contained in R. So if M is so, or in other words, if M is contained in an ideal, then either M is equal to the ideal or that ideal is equal to R. So then now I want to see that what I said in the beginning is true. So it's the following position. So let so R is rings. I and R. So also an ideal I in R is a prime ideal, if and only if the quotient R mod I is an integral domain. And this idea I in R is a maximal idea if and only if R mod I is a field. Okay, so this is the first one is basically directly the definition. So if we take two elements, then the class of A in mod I is equal to 0 if and only A is an element in I. So for I is a prime ideal. No, for our given ideal. So A, B is equal to 0 for two such elements if and only if A times B is in I. So thus R modulo I contains 0 divisors if and only if there exists elements A and B in R which are not in I with AB is an element in I. So this is if and only if I is not a prime ideal. Okay, so this is basically directly the definition. And the second statement is not much more difficult. We'll just take a tiny bit. Second. So let M in R be an ideal such that R mod M is a field. Then it follows that the only ideals in R mod M are 0 and R. So only ideals in R mod M are the class of 0 and R mod M. This we know because in the field we have only the 0 element and R mod M, so these are the only ideals in the field. So this is equivalent to saying that we know we have a correspondence between the ideals in the quotient and the ideals in R which contain the thing you divide by. So the only ideals in R containing M, R, M, and R. And this is an equivalence, because obviously if we divide by M, then this corresponds to, so this is here. And this last statement is obviously equivalent to saying that M is the maximum ideal. So we see that if R modulo M is a field, then M is a maximum ideal. And we can also see that if M is a maximum ideal, we get that these are the only ideals in R mod M. So in order to see the equivalence, we have to see that we can also invert this error. So, I want to show. The commutative ring with 1 whose only ideals are 0, so maybe I call this one A, and A is a field. So let's check this. So let's prove this. So let A be an element in A which is not 0. We have to find an inverse, no? So that means an element B in R with AB equal to 1. So we can look at the ideal generated by A is an ideal in A. And therefore it is either equal to the whole of A or it's 0. But obviously it cannot be 0 because A is not 0. So by assumption A is equal to A. So in particular we have that 1 is an element in A, which, as you remember, is the set of all AB with E in R. So therefore, there is an AB. Okay. Also see as a corollary that maximum ideals are prime ideals. This is because integral domains, fields, fields are in particular integral domains, and so therefore maximal ideals are prime ideals. And just an example. So one thing. So obviously, if so if K is a field, then 0 is a maximum ideal. And if M, so a number, if M is an integer, so say a positive integer, then you can see that M, the ideal generated by M, is a prime ideal if and only if M is a prime number. Okay, so this is clear because it's just saying, by definition of a prime number that, or it's a statement that if you have if a product of two numbers is divisible by the prime numbers, then one of the factors must be, that's an elementary statement. And on the other hand, so it follows that C mod M is an integral domain. But in fact, we know anyway that every finite integral domain is a field, and so this is a field, so this is also maximal. In fact, a field. So, and thus, then, thus M is maximal. So we get the max. So in fact, the maximal, so it turns out that the maximal ideals in Z are precisely the ideals generated by prime numbers. Well, that doesn't follow from what I said. It is. Okay. So these are all simple facts. I just introduced these notions and check their first properties. Now let's look at some other very elementary thing. Let's talk about somehow the divisibility of polynomials. So we want to look at polynomials. We want to investigate how polynomials can divide each other. And this is quite easy to check by something one has learned in school, namely the algorithm of division with rest of one polynomial by another. And so we can do that. Oh, why did I make it? Okay. So first I will maybe talk about the divisibility of polynomials. So let me first define what I mean by something dividing something else. It's kind of clear, but maybe I also want to introduce this abbreviation. So let's say R is an integral domain. So let R an integral domain. And if I take two elements in R, I say that A divides B, and this I write A divides B. If, well, the obvious thing, if B is a multiple of A, so if there exists an element C in R with B is equal to AC. Okay? Very simple. And otherwise, obviously we say that A does not divide B, and we write this as A does not divide B. Okay? So it's clear from the definitions, the multiples of A is just the ideal generated by A, so that A divides B if and only if B is an element in the ideal generated by A. And you can directly see from this, or anyway, see directly that if A divides B and B divides C, then it follows that A divides C, and also if A divides B and A divides C, then it divides, say, the sum or the difference. Now that's quite evident. So, in particular, because however you do it, follows directly. So now we want to consider this divisibility for polynomials. And so for this we look at the division with rest. I mean, I expect you are familiar with it from school, but I still want to introduce it properly. So let K be a field. Maybe. So maybe we can hold it. So I look at polynomial with coefficients in the field. Yes?
What is the reason why we choose integral domain, not just ring?
So for one thing, the way I've written it here, I've put some order, so if I would need at least commutativity. But also, I mean, I just don't like. I mean, one could also say this for, say, a commutative ring, but somehow it's a bit. Yeah. So then, if you have zero divisors, then you have some elements which divide zero. Okay, so maybe that's that's something you can say. But I will only use it in this case, and it behaves in a nice way under the assumption that it's an integral domain. If it's not an integral domain, it's slightly not so nice. So. And you can define it in general, and then you have to see what it does. We only deal with this case. So this is for a theorem. That's a big word, but anyway, so I take the field, and I take the polynomials with coefficients in X. We assume that the second one is non-zero. So it's not the zero polynomial. So they are unique elements. And say Q, which is supposed to be the quotient, and R, Kx, which is supposed to be the rest. Such that I can write F equal to Q times G plus R, and the rest, if it's the rest, it means it should somehow be smaller than G, and this is measured by having a smaller degree. The degree of R is smaller than the degree of G, or R is equal to 0. If you put to the degree of the zero polynomial to be -1, then you wouldn't have made this distinction. Okay. So I explain existence and uniqueness. And so let's first do the existence, which basically amounts to the algorithm of division reversed. So obviously if f is the zero polynomial, or the degree of f is smaller than the degree of g, then I don't have to do anything. So we put q equal to 0 and r equal to f. Okay, so that's not very exciting, so we assume so thus we can see that the degree of f is bigger or equal to the degree of g, and we call this m, and we make induction on f. So we just have to somehow do something to lower the degree of f by 1. And we can conclude and that's somehow more or less obvious. So let A be the leading coefficient of f, and say B the leading coefficient of g, so we just subtract the multiple of g from f so that the leading coefficient goes away. So we put f bar equal to f minus a divided by b times x to the m minus the degree of g times g. Now we see that both summands here have degree m, and the leading coefficient of both terms is a. So it follows, so thus the degree of f bar is smaller than m, or f bar is equal to 0. And in that case we are also done. So we can use induction, or I can say 1 equal to minus 1. So by induction, we can write as here, so f bar is equal to, what do I want to write it? So q prime g plus r prime with r prime is equal to 0, or the degree of r prime is smaller than the degree of g. Well, but then we can easily go back to f. After all, this was just a difference. So we put q equal to q prime plus a divided by b times x to the m minus the degree of g, and r prime equal to R, then F is equal to QG plus R. Okay. So this is directly easy. So, and the uniqueness, so this gives existence, and the uniqueness is also clear. Assume we can write in two different ways, and you can take somehow the difference, and this will contradict our assumptions. So, uniqueness oh yeah, still in one piece. So assume that if F is equal to QG plus R and also to Q prime G plus R prime for some polynomials with the usual assumptions. No? Here above assumptions on R, that the degree of R and R prime is smaller than the degree of G, then it follows we can take the difference, so Q minus Q prime times G is equal to, so we subtract this, R prime minus R, I hope. And so if Q is different from Q prime, then it follows that the degree of Q, so the degree of R prime minus R is equal to the degree of Q minus Q prime plus the degree of G, which is certainly bigger equal to the degree of G. And this contradicts the fact that both R prime and R have degree smaller than the degree of G. Okay, so it follows that Q is equal to Q prime, but then this just says that if I look at this formula now, this is equal to 0, and then R prime is equal to R. Okay, so this was simple, and one should notice it's clear from the definition that this is actually an algorithm. So we have said how we want to do it. So we take our f, we subtract the leading term divided by the leading term times g from it, and then we get a new polynomial and we repeat until we get to the form. So this translates into an algorithm. And so, as an example, I mean, this is obviously something you know from school, but if, say, we have x to the 3 plus x plus 1, and we want to divide it by x plus 1, say, so here the coefficient is 1, so take here x squared, so we have to subtract x to the 3 plus x squared, and so if we subtract we get minus x squared plus x, and so we get minus x, and so this gives minus x squared minus x, and so if I'm not mistaken we get 2x plus 1 and so we take here 2, and so so this is 2x plus 2, and then we subtract that, so minus 1. So this is the quotient, and this is the rest. So you see it's, I mean, you already know, but for completely, this is a very simple algorithm, which you can also, if there is some new polynomials, you can also easily program it, whatever. But anyway, it's a very easy algorithm. So, now we want to use this algorithm of division with rest to also study greatest common divisors of polynomials, because when by repeated division with rest one can find the greatest common divisor of two polynomials. So let me first say what the greatest common divisor is. So definition. We take again an integral domain. And we take A1 to AN elements in R. So an element say R in R is called a greatest common divisor of A1 to N if, so first I just say it is a common divisor if it divides all of them. If A divides, if R divides A1, R divides A2, R divides AN. And it is called the greatest common divisor if every common divisor, if it is a common divisor and every other common divisor divides it. So, a common divisor. R and R of A1 is called the greatest common divisor if every common divisor obviously of A1 to N divides, so S satisfies S divides R. So it is clear that greatest common divisors, so I just write greatest common divisor, abbreviation is greatest common divisor. Clear that this greatest common divisor of A1 to N is well defined up to multiplying by units. Because if we have two greatest common divisors, then one S and R, then S divides R divides S, and so they are obtained one from the other by multiplying by unit. And conversely, it's also clear that both will be greatest common divisors under this assumption. And it's also, we also define, so if 1 is the greatest common divisor, these elements, we say they are relatively prime. Okay. So that means the only elements which divide all these elements are the units. What?
Up to multiplying by a unit element.
Up to multiplying by a unit. But you know, if 1 is the greatest common divisor, that's equivalent to saying that the greatest common divisors are precisely the units. No, by what I said. Yeah.
By element, do you mean element has inverse? Or you
What?
mean an element has inverse? Or you mean
So
one?
to be, I mean, a unit means an element which has an inverse. So, but you know, it's clear that if I have two elements which obtained one from the other by multiplying by a unit, then if one is the greatest common of them is the greatest common divisor of some elements, the other one is 2, because you know everything is divisible by a unit. No, you can just multiply with the inverse of the unit. And so anyway, so this is the mistake. So now we want to look at this in the case of polynomials. And you know, this is also, I think, something you might have seen in school. You know, you just can keep on with two polynomials. You just keep on dividing by the rest of what you had before until there's no rest. And the last thing that you get before this was the greatest common divisor. So is it? Yes. So it's sometimes called Euclidean algorithm, although sometimes also division with rest is called Euclidean algorithm. So we take the polynomials. And so we make some algorithm, say we put R0 equal to F, R1 equal to G, and we can now form the division algorithm. So gives say first F is equal to Q1G plus what I call R2 with a degree of F of R2 smaller than the degree of G, or 2 is equal to 0. So in this F, I can also write this as R0 is equal to Q1 R1 plus R2. And inductively, so now we have defined in R2. Assume we have defined say R0 until I in this way, then and I is still not 0. And then we can redefine I plus 1 I R I minus 1 is equal to Q I R I plus R I plus 1. So again, the degree of Ri plus 1 is smaller than the degree of Ri, or Ri plus 1 is equal to 0. So we can keep on doing this as long as the I plus 1 is not 0. So the algorithm ends when I plus 1 is equal to 0. That means we have that Ri minus 1 is equal to Qi Ri. And the claim is that this, maybe I don't call it I now because it's assume the end at n, so n minus 1 is equal to Qn Rn. So this was a general I, now the final one is n. So the claim is that Rn is the greatest common divisor. Of f and g in the polynomial. Okay. And so we just have to check it. It follows by induction from this algorithm. So first, Rn is a common divisor. F and G. So the equation implies obviously that Rn divides Rn minus 1, and then if you look at the previous one, we have that Rn minus 2 is equal to Q R minus 1 Rn minus 1 plus Rn. So it divides now these two. So yes, Rn divides the right hand side. So thus it follows that Rn divides Rn 2, and in fact for all I, so inductively for all I, so in the formula I minus 1 is equal to Qi Ri plus Ri minus 1, it will divide these two. Ri and Ri minus 1, so it follows that Rn divides Ri minus 1, thus n divides all I, divides all I. In particular, n divides R1, which is G, and n divides R0, which is F. Okay, so it's a common divisor. So here we have kind of started from below and worked our way up. And now conversely, to see that's the greatest common divisor, we come from the other side. So let's say T is Kx, be a common divisor of F and G. So then we can look again, we have F is equal to Q1G plus R1. So F divides, T divides this and this. So T divides two sums. So so the left hand side and Q1G, so it follows T divides R1, and inductively we have I minus 1 is equal to QI plus I plus 1, and T divides I minus 1 and I, thus it follows that T divides I plus 1. So therefore, finally, by induction, T divides Rn. And so it is the greatest common divisor. So this, as I said, this algorithm is sometimes called the Euclidean algorithm. In the moment we will only use a corollary which looks kind of stupid, but it will come handy much later. So when we want to prove an important theorem for Galois theory, you will find that this statement is useful. But here we have this, it's something completely obvious, but I want to state it so that we can use it then. So this is the following statement. So corollary. So let K be a field, so large K be a field, and K is subfield. So by this I mean that K is a field which is a subring of K. No? Where subring means also that the one is the sum. So we have this, and then it's easy to see this is not the corollary, this is just a remark. Then if I take the polynomial ring with coefficients in K is a subring of the polynomial ring with coefficients in large K. This is by definition. Take any polynomial here, put a polynomial there, this is preserved by multiplication. So now we know that polynomial rings are preserved. So now we can look at the greatest common divisor of two polynomials, which happen to be in Kx, in the smaller field. You can either look, but we want to look at the greatest common divisor of these two polynomials in the smaller ring, viewed as polynomials here. In principle, this kind of can depend. Or in a ring, and then so that f and g the elements in X, and let h be the greatest common divisor of these two things in the bigger polynomial. So if whose leading coefficient is in the smaller in the smaller field K, then it follows H lies in the smaller polynomial. Okay, so this is actually quite trivial. So we know we can compute the greatest common divisor. So we can compute a greatest common divisor of these two polynomials by applying the Euclidean algebra. So let L in Kx be the greatest common divisor in Kx computed of f and g, obviously. Via the Euclidean algorithm. Then it follows that L is actually a polynomial with coefficients in the smaller field, because the Euclidean algorithm is just repeated division with rest. If we take one polynomial with coefficients in the field and we make division with rest, then by another polynomial with coefficients in the field, then also the quotient will have coefficients in the same field. It's somehow that we declare that we want to work in this bigger ring doesn't change that fact. It's just the same division with rest. We just compute the coefficients in terms of the coefficients. And so, okay, this is because division with rest stays inside Kx. Okay. Now we know the greatest common divisor of these polynomials in Kx is well defined up to multiplying by a unit. But the units in Kx are the elements, the non-zero elements of K. So it's well defined up to multiplying by elements A in K without zero. So thus it follows that what was this called H is equal to A times L. And so if Ln is the leading coefficient of L, then obviously A times Ln is the leading coefficient. Of H. No, we just multiply. And we have assumed that this is an element in, so that the leading coefficient lies in small k. So dividing, so that means this, so Ln lies in k, and A times Ln lies in k, so A lies also in k. So, by assumption, A times Ln is in small k, and so it follows that A is in k. So that means we have obtained H from L by multiplying by an element in k, and so also H lies in k. Okay, so this is by itself, as I said, it somehow is stupidity. Nobody would care about such an idiotic statement, but you will see that it comes in handy at some point. I will give you enough time to forget it, and then I will suddenly use it. Okay, so let me see. No. Okay. So where are we? Now I want to also, so I had kind of insisted that polynomials are not, I don't want to use them as functions, but obviously we also want to use them as functions. We want to be able to evaluate them at the elements of k, or also in larger rings, and then we also want to talk about their zeros. So, definition. So we take a polynomial f into x, where k is a field. So f, we can write sum I from 0 to n, ai x to the I. So let R be a ring which contains K as a subring. Well, it could be a bigger field, like here. Then let S be an element in R. Then we can define f of s. Just we replace the x to the I by s to the I. Sum I from 0 to n ai s to the I, which is an element in this ring. So we can evaluate f at s. And it is clear, easy to see, that this also defines us a ring homomorphism. So we take f, take the sum of two polynomials, you apply to s. This is f of s plus g of s, you just do the computation. And if we take product of two polynomials, this is f of s times g of s. This is precisely how we have defined the multiplication in the ring, so that in the polynomial ring, so that this is fulfilled. We have this, this rule for multiplication that you say what it does to monomials, and then everything is distributed out. This precisely means this. So thus it follows. So this means thus we have a ring homomorphism. So the evaluation at S from kx to R, which sends f to f of s. So, I mean, this is just ring homomorphism in the sense that it's better with this. It doesn't. I said before, ring homomorphism should send 1 to 1, but this doesn't necessarily do that automatically. So, just a Euro ring homomorphism. So this is called the evaluation morphism. Homomorphism at S. Okay, so this is very. Now we will come back to that later sometime. Now we want to only study something much simpler, namely zeros of polynomials. So, so we want to use this to say that a polynomial with coefficients in a field, for instance, has at most as many zeros as its degree. And so this is the following proposition. So these are obviously things you know, but so let f be a polynomial and A, so in element in case then A is a zero of f if and only if x minus A divides f. And second statement is that if f is a non-zero polynomial, then it has at most as many degrees, as many zeros as its degree.
Doesn't send the unit in the unit?
Not necessarily, no? If I put 1 here, I could get anything. If I put 1 here, I get the sum of the AI. So that doesn't set 1 to 1. But I mean,
the unit of RS is
no, the unit, the multiplicative unit of R is the constant 1 of the it's not 0 has to be sent to 0. That's always the case. But whether 1 is sent to 1, that was an extra condition.
No. And in fact, even when we define the ring homomorphism, we don't assume that the ring is unitary.
No, we don't assume.
So it can be anything.
Yeah, it can be anything. But I had said a moment ago that I wanted to assume that it sends 1 to 1. Yeah. But here I don't want to assume it because otherwise it would,
But I think 1 goes to 1, the 1 polynomial.
No.
Here?
No, it doesn't. So 1.
Because 1 is a 0 is equal to 1 and the rest is 0. Then when we put s, then doesn't matter with
No.
what else we need.
No. If I put, so assume, so for one thing, R doesn't really have to need it, doesn't need 1 in order to define this, but assume R is a ring with 1. Then 1 is sent to some I equals 0 to n, AI, 1 to the I, which is equal to some I equals 0 to n, AI. And that could be anything.
We are taking the polynomial, not the s, or?
What?
We are taking the polynomial f, or?
Yeah, f is a polynomial in x, and then we put s instead of x. And in this case, if we take 1, we put 1. So f of 1 is equal to this. This is just the sum of the coefficients.
Then if we take 0,
If we take 0, we can also get...
no, because if we take...
okay. No, let me just see.
I think we are taking.
No. You are right. I made a mistake. That was stupid. Yeah. It sends 1 to 1. The element 1 is the constant polynomial 1, and that's sent to 1. Okay. So I just said something stupid. So forget it. I mean, clearly. So otherwise it wouldn't even send 0 to 0. Yeah.
Yes.
So I just said something nonsensical. Now I was doing it the other way around. No, you always think that it should be a homomorphism from R
to
to R, but that it isn't. It's a homomorphism. Just if I fix the element, it's an element from Kx to R, and that always works. That's what I wrote. What?
It's written down here.
So it is not homomorphism.
It is a homomorphism. Yes. So this is a homomorphism from Kx to R, and it clearly is. I have said it. The sum of two polynomials applied to S, it's the sum of these. And it also does send 0 to 0. This 0 is the 0 polynomial. And 0 of S is 0. And 1 is the 1 polynomial. And, whatever I put for S, it's still 1. So this is really, and there was no problem. But I was just confused for one moment while I said it, and so I tried to confuse you too. But now, so let's prove this proposition. So, if f is divisible by x minus a, so it means I can write it like this, then obviously if I take f of a by what I said about being homomorphism is equal to a minus a times g of a. And this is 0, so this is 0. Okay. Conversely, if f of a is equal, so let f of a is equal to 0. So obviously, if f is equal to 0, then I can take the other factor to be the 0 polynomial, and it's divisible by x minus a. 0 is divisible by anything. So we'll take put g equal to 0 in this product. So otherwise, I can make division with rest. So I can write f is equal to x minus a times some polynomial g plus some rest. And now the rest is either 0 or the degree of R is smaller than the degree of the polynomial x minus a. This has degree 1, so the only other possibility is that it is 0. So, or a is an element in K without 0. So it just means that R is an element in K. And so A R. So, but then we can now evaluate this at x equal to a. So at x equal to a, we get f of a, which we know is 0, is equal to a minus a times g plus r, because r doesn't change because the element of k. So r is equal to 0. Okay, and the other one, the second one follows from the first. So make induction on the degree f. So if the degree of f is equal to 0, then it follows that f is constant, so f is an element in K, and we have assumed it's not 0, so f has no zeros. And that's certainly okay, because we had it should have at most as many. Okay, so otherwise, so now let f, so let the degree of f equal to n plus 1. So if f has no 0 in K, then the theory of the proposition is right. The proposition is true. So otherwise, let A in K be 0. So that means f goes to 0. Then we can write f is equal to x minus a times g, with g in kx. So by induction, g has at most, so and obviously the degree of g is equal to n. So by induction, g has at most n zeros in K, and so thus f has at most n plus 1 zeros in K. That's a kind of very standard thing. Okay, so this is the statement. And then, so maybe that's enough for today. We see each other next Wednesday, I think, as usual.